Now, as you all are familiar that what like in which categories the elements can be classified, that is the metals, non-metals, and we do have the metalloids, right? So now like we'll be just considering the metals and non-metals, or you can say we'll be differentiating metals and non-metals on the basis of chemical properties, right? That means we will just make metals and non-metals to react with some other element or a compound, and we'll just see that what is the action of this on the given compound or a substance, and what is the action of this on a given substance, and or you can say how we can differentiate among themselves, right? But before we start with the chemical properties, see, you should be familiar with the valencies, because if you are not familiar with the valencies, you won't be able to make the molecular formula of the products, or you can say the any substance which is formed. So you should be well versed with the molecular formulas, right? So before we start, I'll tell you the basic thing that just keep in mind before doing any chemical reaction, not in case of metals and non-metals, or I'm talking in case of any other like in the whole chemistry. Whenever you are doing the chemical reactions, just keep these points in mind, that whenever something reacts with oxygen, it leads to the formation of oxide, right? Respective oxides. Like if we'll just react metal with oxygen, we'll get metal oxide, and if we'll react non-metal with oxygen, we will get non-metal oxide, right? And when we react some substance with water, you know that the crisscross, or you can say the combination that occurs with the hydroxide ion, right? And it leads to the formation of respective hydroxides. Similarly, if some substance react with some halogen, halogen means fluorine, chlorine, bromine or iodine, right? It leads to the formation of the respective halides, means fluoride, chloride, bromide, iodide likewise. So, and moreover, one more thing, if some substance react with hydrogen, then what happens? It leads to the formation of hydrides. See, these are the basic things which you have to keep in mind before starting with the chemical reaction. Now, I'll be just starting with the chemical reaction, and you all know that how we make the chemical formulas. That is, we just write the name of the elements, we write their valencies, and we just intercross them, right? And after just intercrossing or simplifying them, we get the the formula of the compound. So, just look at the board. First reaction which we are considering for metals and non-metals is for reaction with oxygen. Reaction with oxygen, right? As I told you that anything which react with oxygen leads to the formation of oxide. So if I am talking that the reaction of metal with oxygen, obviously it will lead to the formation of metal oxide, and when I am talking about the reaction of non-metal with oxygen, it leads to the formation of non-metal oxide. See, here I am writing on board, so just look at the board. So what happens when metal react with oxygen? It forms metal oxide. It forms metal oxide. See, the formula for this metal oxide can be MO, it can be M2O3, it can be M2O, depending upon that which element or metal we are using and what is the valency of that metal. For example, I am just stating an example for you. Suppose I have the sodium metal, which is denoted by Na, you know that. If I am reacting with oxygen, so what happens? It will lead to the formation of again a sodium oxide with formula Na2O, right? So that means it forms Na2O, right? And now if I take an example of suppose I say aluminium, then what happens? I react with oxygen and I get the aluminium oxide obviously, but the formula is Al2O3. It is aluminium oxide. And moreover, see, I am taking one more example. Suppose I take calcium. So I am reacting calcium with oxygen and again I get calcium oxide, but the formula is CaO, right? So just look at the board and the examples which I stated for you. So you can see that here, or see, all of them are metals. Sodium, aluminium, calcium, all are metals, right? And we are just reacting with the same substance, that is, we are reacting them with the oxygen, and even we are getting the same product, that is the sodium oxide, the aluminium oxide and the calcium oxide. Where is the difference lies? The difference lies in the valencies, due to which you can say the molecular formula of the compound gets changed. Just look at the board how these are formed. See, these are the basic things you should be familiar with in the previous classes, like in 9th, 8th, 7th, but still for just to recall that concept, I am just doing it for you, but I won't be doing in every reaction. So just keep in mind that how I just made this molecular formula. In a similar way, we'll be making a molecular formula for the different compounds in a different chemical reaction. The basic things, or you can say the basic concept which is involved in the formation of the molecular formula remains the same. Right. So just look at the board. When I was combining sodium with oxygen, what I did, I wrote sodium, oxygen with their valencies. Then I interchanged them. So it became Na2O. Right. Similarly, when I reacted aluminium with oxygen, so valency 3 positive, 2 negative, I just interchange it and we get Al2O3. Similarly, when I combined calcium with oxygen, I took calcium and oxygen valencies, interchange, and because they are 2, so we will simplify it and we will get CaO. So this is how how the molecular formula is formed for a compound. Just write the name of the elements with their valency as superscript, just interchange them, and if you can simplify it further, then simplify, otherwise just leave it the same way it is formed. So this is how we get the formula for the various metal oxide. Now, when I talk about the nature of the metal oxide, so you know what is the nature of the metal oxide? As you know that every chemical substance has a certain nature. Either it is acidic, or it is basic, or it is neutral, or we have the amphoteric one, right? So in this case, what is the nature of the metal oxide? So nature of the metal oxide, see, most of the metal oxides are basic in nature. Most of the metal oxides are basic in nature. That means they turn red litmus blue. But we also come across certain metal oxides which show an exceptional behavior, that is, they are amphoteric in nature. They are amphoteric in nature. Right. What do I mean by saying amphoteric? Amphoteric means a substance which possesses the acidic character as well as it possesses the basic character, right? See, if a substance is behaving as an acid, you say that it is acidic in nature. If the substance is behaving as base, so you say it is basic in nature. And you know that any base which is soluble in water is called as alkaline. So alkaline is the category that falls under the bases only, right? And I said neutral. Neutral is that which is neither acidic nor basic with the pH 7. But we have one more category, that is the amphoteric one. Amphoteric is that category in which a substance acts as acid as well as it show a basic character. So as I told you that most of the metal oxides are basic in nature, but few metal oxides are amphoteric in nature. That means they possess the acidic character as well as they possess the basic character. So just look at the board, what are which two metal oxides show this exceptional behavior. So these amphoteric oxides are actually the aluminium oxide and zinc oxide. These two metal oxides are amphoteric in nature. See, this is an important question. You get it for 1 mark, that name amphoteric oxides. So you need to write that yes, the amphoteric oxide is aluminium oxide and zinc oxide. But if you get the question like this, you may get it in under 2 marks, that if there is mention that show how it acts as amphoteric oxide. That means you have to show it with certain chemical reactions, that how it acts as amphoteric in nature. So if you get question like that, so just look at the board how you are going to do it. It is so simple. You just have to react it with an acid and make one more reaction in which you react it with a base. So just look at the board how I am going to show that this aluminium oxide is acidic in the amphoteric in nature. Right. So if I wish to show that aluminium or zinc oxide is amphoteric in nature, see how I am going to show it. I am going to react it with acid. Suppose the acid which I am taking is HCl. And in the second reaction, I need to react it with a base. Suppose I have taken a strong base, that is NaOH. You know that Al2O3 react with both of them, and the reaction with of Al2O3 with an acid and base just indicates its amphoteric nature. So just look at the board, what are the products actually formed? you know that aluminium is going to react with chlorine, and if we just consider the valencies, so it will lead to the formation of the compound with formula AlCl3, that is aluminium chloride, and along with that we'll get water, because you see that H is left, O is left, so obviously we are going to get water. And similarly, when we react aluminium oxide with a strong base NaOH, what we get? We get NaAlO2. And what is the name? It is sodium aluminate plus again the water. This is aluminium chloride and this is the sodium aluminate. Do you got any idea where we did this compound before? Yes, you are right, we did this. This was the first reaction involved in the Bayer's process, that is the chemical separation of bauxite ore of the aluminium. So just you can learn the same reaction and you can use it here to show an amphoteric nature, and obviously we will be using there as a first reaction in the Bayer's process. So this is how you are going to show the amphoteric nature of the aluminium oxide. And if you get it for zinc oxide that show that zinc oxide is amphoteric in nature, then again in a similar manner you are going to react it with an acid as well as with a base. So when we are going to react zinc oxide with an acid, what we'll get? We'll get zinc chloride, ZnCl2, again H2O. And when we are going to react ZnO with the sodium hydroxide, instead of sodium aluminate, what we'll get? We'll get sodium zincate. And what is the formula for sodium zincate? It is Na2ZnO2. So sodium aluminate is NaAlO2 and sodium zincate is Na2ZnO2. Don't get confused that from where this 2 comes in sodium zincate and it is not present in sodium aluminate. It is just a matter of valency, because aluminate is something AlO2 negative and zincate is ZnO2 2 negative. And you know that when we are forming any kind of chemical formula for a compound, we need to intercross the valencies. So same I did in this case. Right. So this is how you are going to show an amphoteric nature of aluminium oxide and zinc oxide. And if you get a question that leaving apart this aluminium and zinc, you will get some other question related to any other metal oxide, like if you get show that calcium oxide, what is the nature of calcium oxide? Then you should know that the calcium is a metal, so obviously metal oxides are basic in nature. And if somebody asks you that how you can prove it, just answer in a fluent way that we can prove it with the help of indicators, as it turns the red litmus blue. So this is how you are going to explain the reaction of metal with oxygen. One question which is striking in my mind, and I want you to know, you are familiar that the sodium and potassium are metals, right? And you know that where the sodium and potassium are stored actually? They are stored under kerosene oil. They can't be stored as such. Like I cannot keep the sodium simply in the air, that means on the table, on the chair. We cannot do that. If we want to store sodium and potassium, we store under kerosene oil. And there is a specific reason for that. You know what is that? Sodium and potassium actually has great affinity to combine with oxygen, as all metals have, but like according to their reactivities, as you know, they are very much reactive as they come, they are the first two metals of the reactivity series. So when they combine with oxygen, they form their respective oxides, and you know this reaction is so exothermic that it leads to the explosion, and we don't need an explosion, right? See, explosion cannot be of constructive use. It doesn't serve any constructive use. So that is why to avoid explosion, we just store it under the kerosene oil so that it does not come in contact with oxygen, and so that there should be no reaction with oxygen, and it will not be forming any kind of oxides, and there won't be any explosion, right? So just for this matter, we store sodium and potassium under kerosene oil. So if you get question like name two metals which are stored under kerosene oil, so what you will be writing? Yes, you will be writing that sodium and potassium are two metals which are stored under the kerosene oil. And if somebody asks you for the reason, what you are going to answer in that case? So you will be writing because sodium and potassium are very reactive. Just note in your copies that as sodium and potassium are very reactive. So when they react with oxygen, they form their respective oxides. or you can say they have great affinity for oxygen, so they readily combine with oxygen to form their respective oxides, and this reaction is so exothermic that it leads to the occurrence of the explosion, and to avoid explosion we just keep it or you can say we store it under kerosene oil in order to avoid it contact with the oxygen. So this is what we have done under the reaction of metal with oxygen. I think it's clear that it will form metal oxides with different formulas, and you know the nature also, you are familiar with the amphoteric one also, and even you can show or indicate the amphoteric nature of certain metal oxides. So this is how we are just going to explain the reaction of metal with oxygen. Now let us see that how non-metal react with oxygen. So what happens? Again we are doing this similar reaction with oxygen. So what happens when non-metal react with oxygen? They form, obviously as I told you, when anything react with oxygen it gets crisscrossed with O2 negative ion and form their respective oxides. So as in this case non-metal is reacting with oxygen, so obviously we will be getting non-metal oxide with for general formula NO. See, again this formula varies, like it can be NO, it can be N2O, it can be NO2, it can be N2O. So it can be anything just depending upon the valencies or just depending upon the stability of the you can say the ratio in which the atoms are just combining. See, I am just stating few examples. So as C plus O2 forms CO2, right? N2 plus O2 forms NO or N2O or N2O3 or N2O5. So likewise, you know that nitrogen is actually an element which show variety of oxides. So you need to be familiar, or you may get a question that name a non-metal which show oxides of different formulas or which show the variety of oxides. So that is the nitrogen oxides, right? That means the combination of nitrogen with oxygen, as it show you can say many kinds of nitrogen oxides, right? So this is how, that means we are going to show that how non-metal react with oxygen. Now if we talk about the nature of the non-metal oxide, so you should know there are two types of nature that the non-metal oxides exhibit. That is, either they are neutral in nature, few are neutral actually, right? Majority of them are acidic in nature. Majority of them are acidic in nature, and if somebody asks you which oxides are acidic, so many of them are acidic, leaving behind the few oxides. And what are those few oxides? That are water, carbon monoxide, N2O, NO. So these are the oxides which are actually neutral in nature, that means neither acidic nor basic with pH 7, and leaving behind these oxides, apart from them the other oxides are acidic in nature, right? And in the similar way we can just explain their action on the litmus, which will be vice versa, like it was turning red litmus blue, so here it is turning the blue litmus red. So this is how you are just going to show that what is the reaction of metal with oxygen and what is the reaction of non-metal with oxygen. I think it's clear to you. Now we'll be moving on to the second property. See, the tip I would just want to share with you, that when you are just making the or doing the chemical reaction, you need to be familiar with the valencies, right? If you are not well versed with the valencies, you won't be able to do a single chemical reaction, even though you know that what will be the name of the product, but still your reaction will go wrong, because if the molecular formula is wrong, everything will be marked as wrong. So just take 10-15 minutes out of your schedule and just get to know the valency chart. That valency chart should be on your tips, right? And if it will be on your tips, you will be just get through all chemical reactions which are involved in whatever way, right? So I am just explaining you the second reaction now. So the second reaction what we are considering is reaction of metal with water, right? So what happens? Again the same reaction we are doing for the non-metals. Right. So reaction with oxygen, the water. So what happens when metal react with the water, as I told you, when something reacts with water, it gets crisscrossed with the hydroxide ion. So same happen in this case. When metal react with water, it just get crisscrossed with this hydroxide ion and leads to the formation of metal hydroxide. Right. In the similar way, the formula can be anything, like I am stating with an example. Suppose I have Na. So when I react Na with water, what do I get? I get again the hydroxide with formula NaOH. And if I react aluminium with water, what I get? Again the aluminium hydroxide, but with formula AlOH whole thrice. And when I react calcium with water, what do I get? Same calcium hydroxide, but formula CaOH whole twice. See, I am stating you different example to just show you that it is not limited that the formula will be only MOH. It can be MOH, it can be MOH whole thrice, it can be MOH whole twice, just depending upon the valency of the metal which is used, because the valency of hydroxide in all the cases is going to remain OH negative. But it is the matter of the valency of the metals that this the molecular formula is just changing for the different metals. Now, the question is that, as I have told you, that whenever the metal react with water, they form their respective hydroxides. But you know what is the difference? That few metals have affinity, you can say a great affinity for water, that they even react with cold water. But few metals are there which react with hot water, few are there which react with boiling water, and few are there which react with steam, and there are few metals which do not react with water under, or you can say with superheated steam also they don't react. So just look at the board, which are those metals. As you are familiar with the reactivity series, right. So this is hydrogen, these are reactive metals, these are less reactive metals. So you know they react, their oxides are not stable, but their hydroxides are so stable. So they react with, even with cold water. These calcium and magnesium react with, means they react with water, that means on heating they react, or we say they react with boiling water or they react with hot water. Aluminium, iron and zinc, they react with steam. And these metals, even they react with steam, and these metals which are placed below hydrogen, they do not react with water in any case. Now what is the reason?